Hello, in this video we are trying to determine the volume of the cylinder. Because we are thinking about the volumes, we need to use triple integral. I'm sorry about my pen. There you go. Triple integral. Okay. So first step is we need to determine the limits of integration. To determine the limits of integration, we need to freeze two coordinates. Determine the limits of integration for the third coordinate. Okay. So for this particular problem, because it's in the shape of a cylinder, we are using cylindrical coordinates. Remember, in two dimensionals, in polar coordinates, at a constant radius, we get this circle, and a constant theta, we have this ray, and the point of intersection between these two is that dot there. But in three dimensionals, constant radius is a cylinder, and a constant theta is, if I put it exactly here, constant theta is this plane. It's no longer a line, it's going to be a plane. Point of intersection between those two, let me film this. I'm actually using my left hand to film this. I hope this is not hard. So point of intersection between these two is along this line here, and it's not just a single dot, it's actually a line. Okay, so once we freeze the radius and theta, we get that line. And how we want to limit the line, determine the limits of integration, because we have z coordinate here and z coordinate here. The line cannot go infinitely. So let us say the z coordinate here is z is equal to 0, and the z coordinate here is z is equal to 5. So the limits of integration would be from 0 to 5. So that line, which is the point of intersection of the constant radius and the constant theta, is limited from 0 to 5. So those are the limits of integration for z. Now we need to determine the limits of integration for the radius. To determine the limits of integration for the radius, we still need to have the setup like this, like about the fruit, constant theta and the constant radius. And now we want to vary the radius. So how far this radius should vary so that it covers the entire radius of this piece. So radius should vary along this line, along this line, along this line, along this line, this line. Let us say the radius of the cylinder is 1. So the radius should vary from 0, which is 0 is actually this line here, and radius is 1 is the last line here. So the radius can only vary from 0 to 1. So when radius varies from 0 to 1, that covers this entire plane. Now we need to determine the limits of integration for theta. So if you look at this vegetable, this is one plane, this is the other plane, this is the third plane. So how the theta is varying is, theta should vary from 0 till 2 pi. Then it covers all these planes, and hence the volume of the cylinder. So 0 to 2 pi. And now the area element is still r dr d theta. So r dr d theta. So 0 to 5, and also dz, because it's a cylindrical coordinate, we also need to have the z coordinate. So because the 0 to 5 is for the z, let's integrate with dz. Integral of dz is z, varies from 0 to 5. So 5 minus 0 is 5. And now we have r dr. Let's not write d theta for now, because these limits of integration are for theta. So r dr, and we want to integrate this from 0 to 1. So 5 r square over 2, 0 to 1. So if you substitute 1, you get 5 over 2. If you substitute 0, you get 0. So that doesn't add to any value. Finally, we have the d theta. So if you integrate with respect to that d theta, you get theta. And the limits of integration are from 0 to 2 pi. So that gives 5 over 2 multiplied with 2 pi. 0 doesn't add to any value. So if you cancel these two, you get 5 pi. So 5 pi is the volume of this vegetable. Thank you for watching. Bye.